Welcome to Electrical Technology. This is Module 4 on magnetism and electromagnetics. On this module, we will learn about the basic principles of magnetism and electromagnetism. The theory of magnetism is explained in terms of magnetic field, magnetic flux, and flux density. Magnetomotive force and magnetic field strength are discussed as a property of electromagnetism. Induced voltage and current on a current-carrying conductor is explained with the aid of Lenz's law and Faraday's law. Let's explain the basic principles of magnetism and electromagnetism. Magnetism and electromagnetism are used in many everyday scientific applications. The uses of electromagnets. Electrical appliances such as your doorbell, electrical fan, relays, motors, electric motors, they work on the principle of electromagnets. An electromagnet is a type of magnet which the magnetic field is produced by an electric current. A current through a conductor creates a magnetic field. The magnetic field disappears when the current is turned off. One advantage of electromagnets is that the magnetic field can be controlled by the amount of current in the conductor. For example, if you increase the value of the current, the field around it also increases. If you drop the value of the current, then the field also drops. Magnetism is one aspect of the combined electromagnetic force. It refers to the physical phenomena arising from the force caused by magnets, objects that produce fields that attract or repel other objects. Magnetic field sources are dipolar, having a north and a south magnetic pole. The north and south pole attract, and the like poles, north and north or south and south, they will repel. When current flows through a conductor, it creates a magnetic field around that conductor, as shown in the picture on your left-hand side. It shows a current-carrying conductor with a magnetic field created around it. The current is represented by the arrow in red, and then the magnetic field is shown by the letter B. You can use your right hand to determine the direction of the magnetic field. Your thumb will show the direction of the current, and then the rest of the fingers shows in which direction is the magnetic field. So in this case, the magnetic field will be in a clockwise direction. So you'll have the magnetic field line rotating around this conductor. On the right hand side, it shows that by winding a conductor into a coil, magnetic field can be made to be stronger. So here you have a stronger magnetic field on the right hand side because you have made the wire into a coil. Now, magnetic fields are also created around permanent magnets. Therefore, movement of a magnet in relation to a conductor results in the flow of current through the conductor. Let's say you have a wire that's winded into a coil, and when you move the permanent magnet inside the coil, a current will be induced on the wire. You can actually measure current that's induced as you move the permanent magnet. Let's look at the characteristics of the magnetic field lines. The direction of the line of magnetic flux at any point is that of a north-seeking pole. Each line of the magnetic flux forms a closed loop. The lines of magnetic flux, they never intersect. The lines of magnetic flux are like stretched elastic cords. The lines of magnetic flux which are parallel and in the same direction, they repel one another. As explained on the previous slide, a current-carrying conductor will create a magnetic field around it. By adding a ferromagnetic ring around the wire, this will increase the flux by several orders of magnitude. Why is that so? Let's look at the picture on the left-hand side. It shows a magnetic flux around a current-carrying conductor with air. Then on the right-hand side, we have a current-carrying conductor with this ferromagnetic ring. So this increases the flux around it. Why is that so? because on the left hand side we have a permeability of air, which is relatively smaller. It's represented by mu naught equals to 4 pi times 10 to the power minus 7 henries per meter. Then on the right hand side, our relative permeability of a ferromagnetic material is about 1,000 or more. The total permeability in a circuit we calculate it by mu, which is equals to mu r times mu naught. Mu r is the relative permeability of the material that we are using, then u naught is the permeability of air. Magnetic flux, denoted by the Greek symbol phi, is a measurement of the total magnetic field lines passing through a certain area. The SI unit of magnetic flux is Weber, denoted by WB, and the formula below is used to calculate the magnetic flux of the circuit. Phi equals to B times A, where phi is the magnetic flux in Weber, A is the area in meters squared, B is the magnitude of flux density in Tesla, T. The magnetic flux density is the amount of flux passing through a certain area that is perpendicular to the direction of the flux, and the formula B is equals to phi over A. So B is the magnetic flux density, which is equals to the magnetic flux divided by the area. The magnetic flux in magnetism is a result of a magnetomotive force where the SI unit is amperes A, which is created when the current flows through a conductor. The picture below shows us that if you have a current carrying conductor that is winded around a metal sheet, then here it shows us the flux direction that is created when a current flows through this wire. So you'll have a magnetic flux that flows around here. MMF in a magnetic circuit is the driving influence of flux around the core. The MMF developed is proportional to the current and the number of turns in which the current is flowing, expressed as follows. MMF is equals to Ni, where N is the number of turns wound over a core which does not have units. The magnetic field in a wound conductor is stronger than that of a single conductor. I is the current flowing through the wound conductor. Other formulas used to calculate MMF in a magnetic circuit are MMF equals to HL, where I is the length in meters of the path of magnetic flux, and H is the magnetic field strength in amperes per meter. Magnetic field strength is defined as the force that creates the flow of lines. MMF equals to S times phi, where phi is the flux and S is the reluctance in amperes per Weber. Reluctance is a measure of how difficult it is to develop flux from MMF in a given magnetic circuit. So reluctance is the same as resistance in an electric circuit. You can also wind your coil around a ferrite toroid. So in this case also you will have a magnetic field that is created here that will flow circular around this ferrite toroid. MMF can be calculated using the same formulas HL or Ni, where H is the magnetic field and then I is the length, is the path length, and then N is the number of turns, and then I is the current in the conductor. The magnetic field strength H and the flux density B at any point in the field are related by the permeability of the material in which the magnetic field is created. Mu is equal to B over H, where mu is the permeability, which is the ability of a material to conduct magnetic lines. Mu is equal to mu naught times mu r. Mu naught is the permeability of air and ur is the relative permeability, meaning that mu naught times mu r is equals to B over H, where mu naught is the permeability of free space SI unit is Henry per meter. It is U naught has a constant value of 4 pi times 10 to the power minus 7 henries per meter. UR is the relative permeability of a magnetic material, which is dimensionless. Relative permeability is dependent on the type of material used in a magnetic circuit. By conducting a ferromagnetic material having a specified relative permeability in a wind current carrying conductor increases the flux produced by the MMF. Reluctance. Reluctance in the magnetic circuit can be compared to resistance in an electric circuit. From electric circuit, the resistance is calculated as follows. R is equals to the EMF divided by the current. So for a magnetic circuit, the reluctance can be calculated as follows. S equals to the MMF divided by phi, which is the flux. Also, it can be calculated as S equals to the length divided by permeability of free space times relative permeability times the area. Magnetic fringing. The spreading of the flux lines outside the common area of the core for the air gap is called fringing. A magnetic circuit may contain one or more air gaps as shown in the figures above. In the air gap, the magnetic lines tend to bow out of the circuit, as shown on the one in the right hand side. Because of the air gap, some of the magnetic field flux lines will bow out. This is called the fringing effect. Now, to calculate the total reluctance of the circuit, for example, if we use an electric circuit to calculate the total resistance, it will be the resistance of the core plus the resistance of the air gap. So in this case, total reluctance of the circuit will be the reluctance of the core plus the reluctance of the air gap. Reluctance behaves like resistors in an electric circuit. Resistors limits the current just like reluctance limits the flux flow. When you look at the metal ring with an air gap, it acts like two reluctances in series. So the total reluctance S total will be equal to S1 plus S2. As soon as flux crosses the air gap, it tends to spread due to the difference in permeability. The longer the air gap, the bigger will be the spreading or fringing. The ratio of the flux in the core to the flux through the air gap is called leakage factor. Leakage factor is the flux in the ion divided by the flux in the air gap. To note, if the magnetic circuit has an air gap and the leakage factor is not given, we assume that the flux flowing in the ion is equals to the flux that is flowing in the air gap. So the leakage factor must be given. If not given, we assume that the two fluxes are equal. Lenz's law states that the direction of the induced EMF is always such a nature as to oppose or neutralize the movement causing the induction. Faraday's law states that the magnitude of the induced EMF is proportional to the rate at which the flux changes or the rate at which the conductor cuts through the flux. Leakages and fringing of flux. On the left-hand side, it shows us a magnetic circuit with an air gap. On the right-hand side, it shows us the leakages and fringing of the flux because of the air gap. Some of the fluxes are leakage via parts A, B, and C, but part D is shown to be expanded due to fringing. So the fringing is caused by the air gap. Thus, the usable flux is less than the total flux produced. Then to calculate the leakage factor, it will be equals to the total flux divided by the usable flux. Now we have a look at this metal ring with three different shapes. So it has an air gap, it has a thinner section, and it also has a thicker section. So for us to calculate the total reluctance, we have to add the three, like just like resistors R1, R2, and R3. So our S1 is the reluctance of air. It will be equal to L1 over mu naught times A, Please note that the air gap has no relative permeability. It only has the permeability of free space. Then the second one will be the reluctance of the thinner section. So it will be L3 divided by U naught times UR. So we include both relative permeability times permeability of free space, then times A. Then the last one will be L2 divided by U naught UR times A. Then we add the three to get the total reluctance. An inductor is a passive element that stores energy in its magnetic field. The ability or inductance is therefore the Henry. The unit for inductance is in Henry, capital letter H, and the symbol to denote inductance is the capital letter L. Same as capacitors, inductors may also be connected in series, parallel, and in a series parallel connection. When they are connected in series, to calculate the total inductance, you add, just like resistors, L1 plus L2 will give you the total inductance. When they are connected in parallel, you will calculate, as we always done when we calculate the total resistance of a circuit. L equals to mu naught times mu R, A times N squared divided by L. This is the equation that is used to calculate the inductance of the inductor, where UR is the relative permeability, mu naught is the permeability of free space, which is a constant, 4 pi times 10 to the power minus 7 henries per meter. A is the area of the free space, unit it's meter squared. N is the number of turns, and then L is the length of the core in meters, and then L is the inductance in henries. Charging and discharging of an inductor. As mentioned before, inductors are a storage device. They store energy in a magnetic field when the electric current flows through it. By connecting an ammeter to measure the current through the inductor, one can see the increment in the value of the current with respect to time. So this is basically the charging of the inductor. Okay, as we did with capacitors, we can't just connect the inductor directly to the voltage source. We have to connect it through a resistor so that we'll be able to discharge it afterwards. Now, when you connect it through a resistor, then you can measure the current through the inductor as it charges through, and then until it gets to the maximum value. This maximum value here of the current, we can calculate it using the maximum voltage divided by the value of the resistor that's connected on the circuit. Then now, after we switch off the power, then the inductor, you can discharge the current. So the discharging part here, that is done after you have switched off the power. Now we have different formulas that we can use. We can use the formulas on the left hand side, which shows the charging current. I will be equals to the maximum current I, open bracket, 1 minus e to the power minus t over tau. So the t there will be the time in seconds at any interval here that you want to calculate, divided by tau. Tau is the time constant, which is equals to L divided by R. In capacitors, tau was equals to RC, but in this case, for inductors, it will be equals to L over R. And then the discharging current will be equals to, that's on the right hand side now, when you're discharging the inductor, that would be equals to the maximum current equals to minus T over tau. What about the voltage? Let's look at the left hand side. For charging voltage, it will be equals to V e to the power minus t over tau. Then on the right hand side, it would be equals to V open bracket 1 minus e to the power minus t over tau. The RL circuit is when a resistor is connected in series with an inductor across a constant voltage supply. The current across the inductor after the switch is connected on terminal 1 increases exponentially from 0 to a final value, where the final value current is determined as follows. I final value is equal to V supply divided by R1. The time constant tau is in seconds. It is the time required for the current to reach maximum steady state value at 5 time constant 5G. Tau is equals to L over R, where tau is the time constant, R is the charging resistor, and L is the inductor. The charging voltage across the current through the inductor are respectively expressed as follows. IL is equals to I final open bracket 1 minus e to the power minus t over tau. That's the charging current. The energy stored in the inductor is equals to half Li squared. The later equation represents the energy stored in the inductor. The discharging current across, this is when the switch is connected in terminal 2, and the voltage through the inductor are respectively expressed as follows. I is equals to Is e to the power minus t over tau. This is the discharging current. And then the discharging voltage, V would be equals to it would be equals to Vt open bracket 1 minus e to the power minus t over tau close bracket. This is exercise 1 from the prescribed textbook. A coil has an inductance of 10 henries and a resistance of 0.8 ohms. The coil is connected to a 20 volt DC supply. Calculate the time constant of the coil. Calculate the maximum value of the current. Calculate the instantaneous value of the current 4 seconds after connected to the supply. Calculate the time taken for the current to reach 12.5 amperes. Calculate the energy stored in the magnetic field when the current has attained its maximum value. Okay, example 2. A coil of 200 turns is uniformly wound around a wooden ring with a mean circumference of 600 millimeters and an area of cross section of 500 square millimeters. If the current flowing into the coil is 4 amperes, calculate number 1, the magnetic field strength, 2, the flux density, C, the total flux. So here we have the number of turns, N equals to 200 turns, I equals to, or the L, which is the length, equal to 600 times 10 to the power minus 3 meters. A, which is the area, 500 times 10 to the power minus 6 square meters. And then I would be equals to 4 amperes. So to calculate the magnetic field strength, H is equals to Ni over L. Number of turns times the current divided by the length. So this is 200 times 4 amperes divided by 600 times 10 to the power minus 3 meters. It gives us 1333 amperes. Then B, which is the flux density. Flux density, remember we said relative permeability is equals to flux density divided by the magnetic field strength. So flux density would be equals to permeability of free space multiplied by the magnetic field strength. So we know that the permeability of free space is equals to 4 pi times 10 to the power minus 7 multiplied by the magnetic field strength, which is 1333. That gives us an answer of 0.001675 Tesla. We can change that to 1675 micro Tesla. Then the total flux is equals to phi equals to BA, which is the flux density times the area. So 1675 times 10 to the power minus 6 multiplied by 500 times 10 to the power minus 6. Okay, thank you. We'll do the exercises from the textbook in class. You are welcome to contact me if you need any assistance.